Hello and welcome to this R tutorial, and mostly welcome to the last part of this course, part 10, model selection and boosting. So in this part we will do two things. First, evaluating our model performance, and second, improving our model performance. And then there will be this bonus section about one of the most powerful algorithms in machine learning, which has become more and more popular, and that is called XGBoost. But first, we want to be able to improve the model performance of all the machine learning models we've built in this course. And improving the model performance can be done with a technique called model selection that consists of choosing the best parameters of your machine learning models. Because remember, every time we built a machine learning model, well, we had two types of parameters. The first type were the parameters that the model learned, that is, the parameters that were changed and found optimal values by running the model. And then the second type of parameters are the parameters that we chose ourselves. For example, the kernel parameter in the kernel SVM model. And these parameters are called the hyperparameters. So there is still room to improve the model because we can still choose some optimal values for these parameters. But since these parameters are not the parameters learned by the model, then we need to figure out another way to choose these optimal values for these parameters, for the hyperparameters. And that's one of the powerful things we'll do in this part 10, and that will be through a very efficient technique called grid search. But before we start grid search, we need to optimize our way to evaluate our models. Because so far, what we did is split our dataset between a training set and a test set, and we trained our model on the training set and we tested its performance on the test set. That's a correct way of evaluating the model performance, but that's not the best one because we actually have the variance problem. The variance problem can be explained by the fact that when we get the accuracy on the test set, well, if we run the model again and test again its performance on another test set, well, we can get a very different accuracy. So judging our model performance only on one accuracy on one test set is actually not super relevant. That's not the most relevant way to evaluate the model performance. And so there is this technique called k-fold cross-validation that improves this a lot because that will fix this variance problem. And how will it fix it? It will fix it by splitting the training set into 10 folds when k equals 10, and most of the time k equals 10, and we train our model on 9 folds, and we test it on the last remaining fold. And since with 10 folds we can make 10 different combinations of 9 folds to train the model and 1 fold to test it, that means that we can train the model and test the model on 10 combinations of training and test sets. And that will already give us a much better idea of the model performance because what we can do afterwards is take an average of the different accuracies of the 10 evaluations and also compute the standard deviation to have a look at the variance. So eventually, our analysis will be much more relevant. And besides, we'll know in which of these 4 categories we'll be. Because if we get a good accuracy and a small variance, we'll be on the lower left one. If we get a large accuracy and a high variance, we will be on the lower right one. If we get a small accuracy and a low variance, we will be on the upper left one. And eventually, if we get a low accuracy and a high variance, we will be on the upper right one. So this k-fold cross-validation is very useful, and besides, our performance analysis is much more relevant. So let's start with this k-fold cross-validation, our first technique of model selection. So since we already built a lot of models, we're not going to build another one. We're going to use one of the models we built and apply k-fold cross-validation on it. And so the model we're going to use is this kernel SVM we made in part 3 classification, and that, remember, we used to predict if the customers are going to click on the ad on the social network to buy yes or no the SUV. So the model is already built and we already have everything. So what we're going to do is take the whole model and we are going to add a new section code inside of it that is going to be, of course, the section code that will implement k-fold cross-validation. So before we start doing it, let's pick the right folder as working directory. So we go to machine learning A to Z, we're now in the last part of this course. Congratulations for reaching it. Part 10, model selection and boosting, and section 48, model selection. All right, make sure that you have the social network at CSV file, and if that's the case, you're ready to go. All right, so now where do we apply the k-fold cross-validation code section? Well, since that consists of evaluating the model performance, well, the most relevant location to put it is right after we build our kernel SVM model. That is right after we build the model. And actually in this code here, we have the predictions of the test set results and the confusion matrix. That is actually a first way of evaluating the model. But as said at the beginning of this tutorial, this is a correct way of evaluating the model, but not the best one. And in today's tutorial, we are introducing a much better way to evaluate our model. And so let's put it right after this section, as in a more advanced performance evaluation method. And so we're going to call this section applying k-fold cross-validation. All right, so now the first thing that we have to do is to install the Caret package, because this contains a very practical tool to create the 10 folds of our training set. So let's start with this, install.packages, and in parentheses and in quotes, Caret. All right, so mine is already installed. We can check it out. Check the same on your list of packages. Here it is, Caret. So I will just put that in comment, but don't forget to install it. And then let's not forget the library command to import automatically the Caret package. All right, and now let's start coding k-fold cross-validation. So first, we're going to create the 10 folds that will divide our training set. And to do this, it's very simple. We're going to use the create folds function by the Caret package to create these 10 folds very efficiently. So let's do it. We're going to call these folds folds. Will actually be a list of 10 different test folds composing our training set. So let's use this create capital F folds function. Here it is. And inside the parentheses, we just need to specify the training set. So here I'm adding the training set. And then we take our dependent variable column by which we want to make the split. You know, it's exactly like when we split the dataset between the training set and the test set. We need to specify the dependent variable to make a split so that the training set and the test set are well distributed according to the dependent variable. Well, here that's the same. We're creating 10 folds of the training set, and we are specifying the dependent variable to make sure are well distributed according to the dependent variable. So that's why here we need to specify our dependent variable, which is purchased. All right, so that's the first argument of the create folds function. And of course, as you might have guessed, the second argument is the number of folds you want to divide your training set into. And really, a good choice of the number of folds is 10, because by creating 10 folds, we will eventually get 10 accuracies, and 10 accuracies is a relevant way to measure the accuracy through the mean of these 10 accuracies. So we will take 10 folds, and I recommend to do that in practice. So here we just add k equals 10. All right, now we're going to implement k-fold cross-validation, because what we just did here is just to create the folds, but now we need to implement the algorithm itself. And to do this, well, there are several ways of doing it, but we're going to use a very practical function in R, which is called the lapply function, and that consists of applying a function to the different elements of a list. So this list is going to be our folds list that contains the 10 test folds, and the function is the function that is going to compute the accuracy for each of these 10 test folds. So let's start by creating a new variable that we're going to call CV, and then let's use here this lapply function. All right, and you're going to understand what's going to happen. So in this lapply function, we need to input two arguments. The first argument is the list of the elements to which we're going to apply the next function, which is the next argument. And so, as I just said, this list is folds, the list of our 10 test folds. And then the next argument is the function. So a function in R can be written this way. Function, then in parentheses we need to input the argument, which we will call x. This is a local argument so far, but x is actually going to be each one of the 10 test folds. So x here, and then a pair of brackets. Here we go. And inside these brackets, we are going to implement this function that will compute the accuracy of the model on each of these 10 test folds. So basically in this function, we are going to implement k-fold cross-validation. So what do we need to implement k-fold cross-validation? Well, first, we need the training fold. The training fold is the whole training set to which we withdraw the test fold. So basically, training fold here, I'm creating a new local variable actually that I'm calling training fold. And so as I just said, this is the whole training set. Here we go. But to which we withdraw the test fold. That is minus x. Because you know x is actually each element of this folds list here. So by putting minus x here, we are taking the whole training set, but without the test fold. And therefore, that's actually the training fold. And then comma to take all the columns. All right, so we got our training fold. Now let's get our test fold. So our test fold, try to guess what it's going to be. Test fold equals training set. And inside the square brackets, well, what do we need to put here? Well, that's actually x. Because you know, x represents all the observations for each one of the 10 test folds. So we got our test fold. And then what do we need to do now? Now what we need to do is train our kernel SVM model on the training fold, and then we will test its performance on the test fold. So basically, what do we need to do now? We need to add our model, which is our kernel SVM classifier. So what we can do now is just take this code section here, because that's where we build the model, and we need to include this model in the function. That's why we're taking it. So copy, and let's add it here. Paste. And here we go, we have our model. But we're not training this kernel SVM classifier on the training set. We're training it on the training fold, because that's the principle of k-fold cross-validation. We are training our classifier on each one of the 10 training folds. So that's why here we're taking the training fold, and that we create here inside this function that we're making right now. And then we keep the same argument. All right, then what do we need to do? Well, that's exactly the same as what we're doing when we make a model, that is predicting the test set results. That's the next step, because that's from this test set results that we will then compute the confusion matrix, and therefore the accuracy, which is exactly what we need. That is, which is exactly what will be returned by the function we are making right now to implement k-fold cross-validation. So same, let's copy this line to predict the test set results, and let's copy it here. And is that all? Of course no, because we are not testing our classifier on the test set, but we're testing it on the test fold, right? Because you know we are training our model on the training fold and testing its performance on the test fold. So now that's good. And now let's move on to the next step, which is to compute the confusion matrix. So still, let's take this line here and let's paste it below. Right here, paste. And now, of course, we need to change test set and replace it by test fold. All right, and this will give us the confusion matrix of this classifier SVM model, of this kernel SVM classifier, and that is trained on the training fold and tested on the test fold. And therefore, this line of code will give you the confusion matrix for the observations of the test fold. All right, and now last step, we need to compute the accuracy because we're doing all this to get the accuracies for all the 10 test faults here. So let's compute the accuracy. The accuracy is, we've calculated this accuracy many times. We take the number of correct predictions, which is CM1, 1, because this corresponds to the number of correct predictions of the first class, plus CM2, 2, because this corresponds to the number of correct predictions of the second class. And since we have two classes, this sum corresponds to the total number of correct predictions. And then we divide it by the total number of observations in the test set. And therefore, that's the number of correct predictions, which is this sum here, to which we also need to add the number of incorrect predictions. And therefore, we can copy this and take the first number of incorrect predictions that corresponds to the first class and the second number of incorrect predictions that corresponds to the second class. And so here we are actually taking all the elements of this confusion matrix, that is the number of correct predictions plus the number of incorrect predictions. And so now with this line of code we get the accuracy for one fold, but since we're using this lapply function, this will do all this, compute the accuracy for each of the 10 test folds, and therefore we will get 10 accuracies and we will compute its mean, which will give us a much more relevant accuracy than just a single one we obtained earlier with our previous method of evaluating the model performance. Alright, so now we have everything, but we just need to specify that we want to have this accuracy returned because this is a function, so we need to specify what we want this function to return. And to do this, we just add return parenthesis and accuracy. And now everything is ready. K-fold cross-validation is well implemented. Alright, so now we're ready to get the 10 accuracies that will result from this 10-fold cross-validation technique. So we're going to select everything from here up to the top because we haven't imported the dataset yet. So let's press Command and Control plus Enter to execute the whole thing. Here we go. Everything was correctly executed in less than 1 second. So that's perfect. Let's have a look at the results. So first let's put that down. Alright. So here we get all the results. First, the dataset was well imported, was split into the training set and the test set at this section here. And then we build our classifier, which is our kernel SVM classifier. And of course, we get our CV list that we built through K-fold cross-validation. That is this CV list, which is the list of the 10 accuracies that result from K-fold cross-validation. And so let's check it out. Let's have a look at what these 10 accuracies are. So we're going to look at it from the console. So I'm pressing CV here and pressing enter. And here we go. That's the results. That's the 10 accuracies. So fold 1, we get a 93% accuracy. That's very good. Fold 2, 87%. Fold 3, 100%. So no incorrect prediction. Fold 4, 86%. Fold 5, 96%. 90% on fold 6, 90% on fold 7, 93% on fold 8, 90% fold 9, and eventually 83% on fold 10. So that clearly illustrates what I told you about this variance problem that can occur when we rerun the model several times, because indeed we get different accuracies and sometimes a large difference in accuracy from one fold to another. So from here to here, that's fine. But here, for example, from fold 2 to fold 3, we get a 13% difference of accuracies. So that's why it's not that relevant to compute the accuracy on one single split. And it's much more relevant to compute the accuracies on 10 splits, because then we can take the mean. And that's exactly what we are going to do right now. We are going to compute the mean of the 10 accuracies that we obtained here. So to get this mean, it's actually very simple. We're just going to use the mean function, so parenthesis here, and inside this mean we of course input CV, because CV is the list of our 10 accuracies that we obtain here. However, just to make sure we get the values of the accuracies of each of the 10 folds, we need to specify here as dot numeric, and in parentheses we include CV, to make sure we take the mean of these values here that are the accuracies. And let's put this average of the accuracies into one variable that will appear in the values here, and let's call this variable simply accuracy, because the mean of these accuracies is just the ultimate relevant accuracy. So accuracy equals mean of the accuracies in this CV list. Alright, so let's compute it, and we'll get, let's see, an accuracy of 91%. And that's the relevant accuracy we're looking for. So overall, we can say with more credibility that our model, our kernel SVM classifier, is pretty performant. So that's pretty good, and now congratulations, you have a much more advanced way of evaluating your model performance in your data science toolkit. But you'll see, in the next tutorial we'll see a very powerful technique that will help us choose the optimal hyperparameters of any machine learning model we build. So I look forward to doing that in the next tutorial.